Hello, this is FlippedHarber for Precalculus. In this video, we'll go over Section 2.5, Mathematical Models, Constructing Functions. The objective for the lesson is to construct and analyze functions. Now what we're going to do in this video is go through some story problems from the same pages as your homework. Each of these examples comes from the problem right before or right after your homework questions, so you know that they're on the same topic. Number 4, the price P and the quantity X sold of a certain product obey the demand equation P equals negative 1/3 X plus 100. We're stated that the domain is between 0 and 300 units. Part A expressed the revenue R as a function of X. Then they ask what is the revenue if 100 units are sold. Then they ask us to graph the revenue function using our graphing calculator. Using that graph, we need to determine what quantity X maximizes revenue and what is that maximum revenue. And then finally, what price should the company charge to maximize revenue? So we're going to end up plugging all the way back into our original demand equation, P. Alright, let's get started with the revenue function. Revenue, that is that the money that a company takes in is equal to their price multiplied by how many units they sell. So we take the demand equation P and multiply it by X. Distributing the X in, we get the function negative 1/3 X squared plus 100X. Now part B, what is the revenue if 100 units are sold? We're just going to find R of 100. And we find out that it's $6,666.67, obviously rounding to cents. Now if we type the equation R, the negative 1/3 X squared plus 100X, into our calculator, we'll get a graph like this. Now I've set up the window to fit this data perfectly. I used the range that they gave us from 0 to 300 for the X values, and my window actually tops out at 7,500. You might want to go a little higher on that window, but I've also hit the trace feature on the calculator, and I've moved the cursor over so that it's at the very top of the parabola. So we can read off that our maximum Y value, that is that our maximum revenue, is $7,500. Now that's actually why they had us plug in 100. They wanted to give us a sense of how big this revenue could get. And I can also read off from my trace that the company has to sell 150 units in order to maximize that revenue. So our answers for part D, what quantity maximizes revenue? Well, 150 maximizes the revenue. What is the maximum revenue? $7,500. So for part E, what price should the company charge to maximize revenue? We take 150 and plug it all the way back into our P function, and we find out that the company should charge $50 for each unit. Okay, let's move on. Number 7, David has available 400 yards of fencing and wishes to enclose a rectangular area. We need to express the area A of the rectangle as a function of the width X of the rectangle. They want us to talk about the domain of A, and then finally take that function, put it into our graphing calculator, and find out what value X is the area the largest. So first of all, we know that it's a rectangular field. The width is X. I've labeled that in a picture. Now if you stop and think about this, if the top and bottom of this rectangle are both X, then what's left for the two sides is 400, the total yards of fencing, minus 2X. So each side is half that, 200 minus X. Now I can simply find the area by multiplying X times 200 minus X, and I get my area function. A of X equals 200X minus X squared. Now what's my domain for A? Well, what's the biggest number and the littlest number that I can plug in for X? Well, if David were not that bright and he were to string all of his fencing out for 200 feet and then come all the way back, he's used up all 400 yards of fencing, but he hasn't made a field big enough to put anything in. So those two extremes represent our domain for this function. X can be all the way down to 0, and it can go all the way up to 200 yards. Okay, so let's graph this thing. We plug it into our calculator, we hit the trace feature, and we can find the very top of this parabola, and we find out that the value of x that makes the area the largest is 100 yards. Now really what that means is David should make a square field. Squares have the largest enclosed area. Okay, let's move on to our next problem. Let P equal the generic point xy on the graph y equals x squared minus 8. For part A, express the distance d from the point P to the point 0, -1. So we're talking about a distance between a point on a curve and a very specific point as a function of x. Then they want us to plug in two values and find out what d is. What if x equals 0? What if x equals -1? Now, the reason that they do this is to help us get a sense of how big this distance can be. How big should I make my window when I do the next part, which is to use my graphing calculator to graph that function. And then part E, I'm again going to use that trace feature of my calculator in order to find the smallest distance. Okay, so let's get started with my distance function. Now I know my distance equation. It's a form of the Pythagorean theorem. My 2 points are xy and 0, -1. So I go ahead and go x minus 0 and y minus a -1 in my 2 parentheses. But I make a substitution. What I do is I substitute in x squared minus 8 for y. So my distance function is the square root of x squared plus the quantity x squared minus 7 squared. Now, here's a little tip from me to you. You're going to be typing this into your calculator. We don't really need to go through a whole lot of simplification. If you want to FOIL out that x squared minus 7, it's not that bad. It's just x to the 4th minus 14x squared plus 49. But you can leave it just like this. You can type it in just the way it looks into your calculator and it will do just fine. So let's go ahead and do B and C. What if x equals 0? What if x equals -1? So we're finding d of 0 and d of -1. Now when d of 0, I get a nice number. I get 7. With d of -1, it's not so nice. It's a square root of 37, which is a little bit bigger than 6. I'd actually just leave it as the square root of 37. A lot of people like to plug it in. Go ahead, plug it in, whatever. Okay, let's graph this function. So again, I typed it in just the way I have it up there on that top line. I didn't bother to multiply it out. I didn't bother to simplify. I get this weird W shape. Now since we're looking to find out where d is the smallest, I turn on my trace feature and I find the bottom, or at least one bottom, of the W. And I see that x equals -2.55. So the other side of that W would be where x is equal to a positive 2.55. If you don't believe me, go ahead and just hit the right arrow until that cursor's at the bottom. Okay. Let's move on. Number 20. An open top box with a square base is required to have a volume of 10. They need us to express the amount A of material used to make such a box as a function of the length x of a side of the square base. They want to know how much material is required for a base 1 by 1, how much material is required for a base of 2 by 2. They want us to again graph it in our calculator and figure out what value of x is A the smallest. Now, an open top box would be like a shoebox without the top on it. So there's only a base and 4 sides to talk about. So the area is x squared, the area of the base, plus 4, because we have 4 sides that are x wide and 10 over x squared tall. Where did I get the 10 over x squared? Well, they told us that the volume had to be 10. That's how I came up with that expression. So simplifying it, a of x is equal to x squared plus 400x. Parts B and C, they want us to plug in 1 for x and plug in 2 for x. So we're finding a of 1, that's equal to 41. A of 2 is equal to 24. So if we make our box bigger on the base, we're going to use less material to make that box. But there's going to be a swing in this curve, and if we make our box too wide, we're going to be wasting material. So if we look at our graph and again use the trace feature, I find the lowest point on this curve is at x equals 2.76. So that's the value that will make the area the smallest. Alright, number 24. They give us a picture for this. They tell us a rectangle is inscribed in a semicircle of radius 2. They say let P equal some generic point xy. It's in the first quadrant, and it's not only the vertex of the rectangle, but it's also on that curve. Now that's nice because they also tell us an equation for this semicircle. It's y equals the square root of 4 minus x squared. I will be using that. They want us to first express the area A of the rectangle as a function of x. Then they want us to express the perimeter P of the rectangle as a function of x. So where the heck is x in my picture? Well, yes, it's the x coordinate of that point up there in the upper right hand corner of the rectangle, but x is how far that point is from the y-axis. So you could look at the picture, and x is the distance along the bottom of the rectangle from the middle of the rectangle over to the right side. So the base of that rectangle is 2x. X on one side of the y-axis, x on the other side of the y-axis. How tall is that rectangle? Well, it's y tall, but we can plug in something for y. So my area is 2x, that's the base of the rectangle, times y, the height of the rectangle, but I substitute in my square root of 4 minus x squared for y. So I've got my area equation. Now my perimeter equation, I just need to add up all four sides. The top and bottom are both 2x. Add them together, that's 4x. The left and right sides are both y. Add them up, it's 2y. So the perimeter is 4x plus 2y. Again, I substitute in what y equals to get a function of x. I want to graph these two and find out what x value makes the area the largest and what x value makes the p the largest. Not necessarily the same answer for both questions there. So here's my graph for the area A. And again, I just simply use the trace feature, move the cursor over to the top of the curve, and the x value that makes the area the largest is 1.436. Looking at my perimeter graph, I want to maximize the perimeter, and that happens when x equals 1.78. Now, you might be asking yourself, why did both of these graphs stop? Well, if you plug in too big of a number, that is, if you plug a number bigger than 2 into the equation, you can't take the square root anymore. So the domain of this function stops at 2 in both cases. Alright, number 28. A wire 10 meters long is to be cut into two pieces. One piece will be shaped as an equilateral triangle, and the other piece will be shaped as a circle. They want us to express the total area enclosed by the pieces of wire as a function of the length x of one side of the equilateral triangle. They want us to find the domain of the area, and they want us to graph it and find out what value of x makes A the smallest. So I've got my two shapes, an equilateral triangle and a circle. The equilateral triangle has 3 equal sides, all of them x. Now if I use that much of the wire to make the equilateral triangle, that leaves 10 minus 3x to make the circle. So that's the diameter, excuse me, not diameter, that's the circumference of the circle. So my area is x squared times the square root of 3 over 4. Now basically what I did there is I looked up the area for an equilateral triangle, plus the area of that circle is the circumference squared divided by 4 pi. Okay, I did do that right, even though I labeled it D. That equation is correct. Now what's my domain for A? Well, the smallest amount that I could use for the equilateral triangle is to use none of it. I could have x be 0 and use all 10 meters to make that circle. The most that I can do is if I use all of the wire to make the equilateral triangle. So my domain is that x has to be between 0 and 10/3. That would be no equilateral triangle, all circle, all the way up to all equilateral triangle, no circle. Okay, so now let's graph this. So we see that we have an area that starts out at a certain value. So if we have all circle, it's got a certain area. The area drops down, it bottoms out, and then the area picks back up, and then it stops when the function has met, all equilateral triangle. So we're looking for the smallest area, which is at the bottom of this curve, and that happens when x equals 2.085. So if we make the equilateral triangle 2.085 on all 3 sides, that will give us the smallest area contained. Okay, so this was a lot. Okay, these are not easy problems, but once you get the function, it should all be downhill from there, because once you get the function, then most of it's calculator work. Okay, so give them a shot. Maybe you need to go back and look at another problem again. You've got your homework, and I'll see you in class, and I'll see you online.